Okay, we are now recording. All right, welcome to class. Again, let me just ask one last time before I start into the material here. Does anybody have any question or questions about the assignment or the books or anything at all? You can either voice your question or you can type it in the chat box. And I'm not seeing or hearing anything, so let's move on. Okay, so first I'm going to talk about the assignment that was due 10 minutes ago. The vast majority of you turned in the assignment and did it very well. I did have to dock a few of you some points because of various things. The most important thing that I docked you for, and the thing that I docked you the most points for, was if you didn't include the equation. A lot of you sent me a copy of your graph, but then you didn't show what was the equation of the curve that fit the data the best. That was an important part of the assignment. So hopefully you figured out that it's possible to upload the file and also type the equation into the text box. A few of you said that you had trouble with that, and I'm perplexed as to why you had trouble because everybody else did it. Those of you that found that you couldn't type the type anything in the text box at the same time as you uploaded the equation, were any of you in that category? If so, can you speak up and tell us?
Yeah, I was. So I clicked on file upload and uploaded the PDF. And then I went over to text box and typed up the equation.
Yeah.
And then I clicked submit and it only submitted the text box.
It did the same for me, so I ended up just putting the equation in comments instead of the text box, and then I was able to submit both of them.
Oh, okay. Yeah, that makes sense. Okay, put it in the comments. Yeah, okay, that's a good solution. The teacher version of Canvas is slightly different than the student version, and so I don't see those little subtleties. Yeah, thank you, Julia. Yeah, so everybody, please do that in the future. If you need to type in any text, put it in the comments section rather than text box, and it should work out well. Okay, now I did have a couple people who uploaded the equation but didn't include the graph. Okay, so that obviously needed to be done differently. Some of you ran into the problem that Max described, and I was really glad to see that you came up with creative solutions for how to get around it. One person just did a screenshot of the whole thing. So they had the graph over here, and over on the left side, they had the equations and everything showing there. That was a good creative solution. I love creative solutions. You guys are going to figure that out real quick. Let's see. One person figured out how to write the equation as part of the graph. That was really cool. So kudos to you for doing that. Yeah, there's lots of different ways you can get the job done. Now, I did have to take off a few points for some people. On some of the graphs, the data was all scrunched together. And this is something that I specifically warned you about. Let me just open up my whiteboard here. So hopefully you remember. Let me get, I got a bunch of windows that you guys don't have, and some of them are getting in the way here. Okay, so hopefully you guys remember that I specifically told you that if this is the page and here's your graph, I don't want to see all the data scrunched up in one little part of the graph. I want the data to fill the page, okay? So if you did that, I docked you some points. And also, some of you didn't label your axes, and I specifically asked you to label the axes. So I docked you a little bit for that, not much, but I docked you a little bit for that. And also I noticed that several of you, it didn't look like you did multiple runs. Again, let me turn on the whiteboard so I can show. So what I was hoping to see was, okay, so here are your axes. So I was hoping to see a bunch of data points where I have different y values, all for the same x value. And then over here, I have a couple more data points. And then over here, I have a couple more data points. And over here, I have a couple more data points. Okay. So I was hoping to see multiple data points for each of your independent variable settings. And many of you did that. So thank you for that. But a lot of you, I only saw one data point there, and that was not quite what I wanted. And let's see, anything else on my notes here? I think that's pretty much it. Okay, so hopefully you guys are more comfortable now with how to graph data, how we run experiments. Hopefully you're more familiar with the idea of a direct versus inverse relationship, and more comfortable with the idea of a linear versus nonlinear equation. Because we are going to continue with that today. In today's assignment, we are going to definitely look at the same thing. We're going to ask the questions, do we expect this to be direct or inverse? We do expect this to be linear or nonlinear, but in a different circumstance. So again, before I start into today's assignment, let me just pause. Anybody have any questions?
Yes. So I'm just wondering, I did the equation, I put it in the graph, but I guess I didn't know you had to submit it through the text box or comments. So can I just resubmit and put it there and I'll get full credit still?
Yeah, thank you for bringing that up. Yeah, normally I would say that once the deadline has hit, then I don't allow resubmissions, but this is the beginning of the year and maybe I didn't make myself as plain as I probably should have. So I am going to make an exception. Don't get used to this. Okay, I'm not going to do this as the year goes on, but I will allow resubmissions this time around. Okay, so if you look on Canvas and you see that you didn't get the full points, which by the way is 10 points, if you didn't get the full 10 points, go ahead and correct what was wrong, resubmit it, and I will give you credit. And I won't count it as a late assignment, provided you submitted something before the deadline. Now, if there's a few of you that didn't submit anything before the deadline, and so if you go in and submit it now, that is going to cost you a late pass. And by the way, I hope you guys all know that in the disclosure, I talked about this. Everybody's allowed 2 late passes per term. So what that means is I will accept 2 late assignments and I'll give you full credit for them because I understand, things happen. Yeah, I'll give you full credit for 2 late assignments, but after that, I can't give any points for late assignments. So thank you for asking that, Lucas. All right, so let me open up Canvas and we're going to look at today's assignment. Some of you may have noticed that I've already put it on Canvas. Okay, so hopefully you guys are now seeing sorry about that. Okay, so hopefully you guys are now seeing my Canvas screen. And so let's click on physics. A little bit slow here. Let's go into the assignments page. And you're going to see 2 assignments that weren't there last week. Flat Earth assignment part 1, flat Earth assignment part 2. So today we're going to do part 1. On Wednesday, we'll do part 2. And so let's click on part 1, see what it looks like. Now my thing looks a little different than yours because I'm a teacher, you're students. So let me click on preview. So that'll make it look a little bit more like what you will see when you click on it. And hopefully you guys are seeing, let me enlarge this a little bit here. Hopefully that's the person that you recognize. So what is that thing that I'm holding in my hand there? Anybody recognize what that is? Let's see, my chat box. When I start sharing my screen, my chat box goes away. So if you're typing into the chat box, I can't see you. So anyway, what I'm holding in my hand there is a certificate, a membership certificate to the Flat Earth Society. And that is, and by the way, that's if you look at the name on the certificate here, okay. Okay, so the name right there, that's me. I actually am a member of the Flat Earth Society, which surprises a lot of people. How in the world could a physicist be a member of the Flat Earth Society? Well, it's fun. I enjoy trolling people. And that's basically why the Flat Earth Society exists. Is we love to troll people, and we love to challenge you, and ask you to prove that the Earth is not flat. And you would be astounded at how many people can't do that. In fact, I got to turn off annotating here. Hang on a second here. Let's clear that first. Okay, so, all right. So our first little activity here is basically that. George Bernard Shaw is a name that I hope you guys have heard before. You may not know much about him. As far as I know, he wasn't actually a member of the Flat Earth Society, but he asks the same questions that me and my friends in the Flat Earth Society ask. So let me pick one person here. How about Kennedy? Would you be willing to turn on your microphone, please, and read to the class what you see on the screen here, this quote from George Bernard Shaw?
We are more gullible and superstitious today than we were in the Middle Ages. An example of modern credulity is
okay, so let me interrupt for just a second. So credulity is a word that most people don't know. Credulity is basically the same thing as gullibility. So if people believe what they're told without even questioning it, that we say they're gullible, or we say that that's an example of credulity. Okay, so sorry to interrupt, Kennedy. Go ahead and finish, and start again with an example of.
Okay. An example of modern credulity is the widespread belief that the Earth is round. The average man can advance not a single reason for thinking that the Earth is round. He merely swallows this theory because there is something about it that appeals to the 20th century mentality.
Okay, and in my experience, I found this to be very true. Pretty much all students that come into my class, if I ask them if the Earth is flat or round, they all say that it's round. But if I ask them to prove that it's not flat, very few people can come up with a good reason for believing that the Earth is not flat. So this is the first thing that I want you to do. And this is question number 1 on your homework tonight. Now, I'm not going to spend a lot of time on this right now because we have more important things that we need to get into, but let's just talk about it. What I'm going to ask you for question number 1 in the homework tonight is to please list as many reasons as you can, or at least one. Please find at least one, but preferably more. A reason for why we should believe that the Earth is round. Okay? Because I think it's flat. Wink. Now, those of you who are taking notes, I want you to note that I winked when I said I think it's flat. Okay. All right. So me and my friends of the Flat Earth Society, we think the Earth is flat. And we have a good reason for thinking that. I mean, it looks flat. Now, here in Utah, yeah, it's hard to say because there's so many mountains. But if you go to Kansas, or if you go to West Texas, or if you go out on the ocean, the Earth looks flat. And it just makes good sense that it would be flat. I mean, this whole thing about, the people down in Australia, they're upside down relative to us, that's crazy talk. I mean, that doesn't make sense. Wink. Okay. So when you fill in the answer for question number 1 on the homework tonight, I want you to list a bunch of reasons for why you think it's flat, and do not rely on measurements or observations that other people have made. Okay, it has to be a measurement and observation that you yourself could make. Photographs taken by NASA astronauts, they're not acceptable because, NASA might be part of Obama's deep state conspiracy here. So we obviously can't trust them. Okay, so only trust or only include observations or measurements that you yourself could do, and only include things that you could do without leaving the state of Utah. That's an important restriction that I want to put on you, because if you do, there are places where you could go that you could do it pretty easily. So I'm going to put the restriction that you can only do it without leaving the state of Utah, and it has to be something that you yourself could do. So if you look on Canvas, you'll see there's a text box here where you can put in your answers. But let me just pause for a second. Can anybody think of anything off the top of their head that would be evidence that the Earth is not flat? that you yourself could do without leaving Utah.
So I don't know if this works. I think it works, but like if you get in a plane, technically you could stay in Utah, but you can still kind of see it's curved just a little bit. I think
Okay,
that counts.
I see where you're coming from. Now, me and my friends in the Flat Earth Society, we think, wink, okay, that the Earth looks like this. You see that picture right there? Okay, so we think that the Earth is a disk. And I don't want to go into too much detail here because we got a lot we have to do today. And if we get bogged down in this, we won't finish all the things we want to do today. But I encourage you to go to the Flat Earth Society website. It's pretty cool. It's a lot of fun. So what we supposedly believe, wink, is that the Earth is a great big disk. And the North Pole is in the center of the disk. So again, let me turn on annotations here. Okay, so right here, oh boy, that didn't show up. That color doesn't show up very well, does it? Okay, so right there is the North Pole. Okay, and all around the edges here, this is Antarctica. And so it's basically an ice wall. So if you leave from the North Pole and you sail south, you keep going south, eventually you'll get to Antarctica. And it doesn't matter which way you go, because Antarctica, it's a great big wall that surrounds the Earth. And by the way, me and my friends in the Flat Earth Society, we are really worried about global warming, because if the Earth continues to warm up and the ice melts, then the ice wall that keeps all of the water in place, that's going to melt, and all the water is going to fall off the edge here. And that's going to be a terrible disaster. So global warming is an even bigger problem for us in the Flat Earth Society. Wink. Okay. So anyway, Lucas, the reason I bring that up is because this is what we would say. So if you get up in an airplane and you say, well, I can see the curvature of the Earth, what me and my friends in the Flat Earth Society would say is just that you're seeing the outer edge of the disk. Okay. What you're going to find is that we in the Flat Earth Society, we have interesting comebacks for a lot of the arguments that people make. Okay, so I don't want to go into any more detail on this because otherwise we'll run out of time. But this is an assignment that you guys, or this is question number 1 on the assignment. So I want you to find at least one, but preferably more. And it has to meet all these conditions that I put here. Okay, has to be stuff that you yourself could do without leaving the state of Utah. All right, now this is only one question out of 15 possible. So if you can't do this one, don't sweat it. You're only going to lose 1 out of 15 points. Not going to be a big deal. All right, so let's go on to the next question in the homework assignment today. Okay. So, by the way, you guys, you see that hat that I'm wearing, the tinfoil hat? Keep that in mind. We're going to talk later in the year about tinfoil hats and what they are. But note that I'm wearing that. It kind of gives you an idea of the kind of Flat Earth Society conspiracy theories. Okay, so what we're going to do today is we're going to spend the whole class period focusing on just one of the arguments that could be made for why the Earth is flat. Okay, now me and my friends in the Flat Earth Society, we're going to argue against this, but this is one of the arguments that people sometimes make for why they say that the Earth is, or why they say the Earth is round rather than flat. Did I say that wrong a minute ago? I may have. All right, so sailors and other explorers have known for a long, long time that if you get in a boat or if you just walk and if you head south, and every night you look at the North Star, which, by the way, I hope you guys can all find the North Star. At the end of the class period, if we have some time left over, I'll show you how to find the North Star. But it's long been known that if you head south, and then every night you look at the North Star and you find out how high it is above the horizon. So you point one arm at the horizon, point the other arm at the North Star. And so then the angle in between there, that angle gets smaller and smaller and smaller. The North Star gets lower and lower in the sky the further south you go. And then at some point it just disappears completely. Okay, so Polaris is the official name for the North Star. So that's what I'm going to start calling it now. Okay, so the people who think that the Earth is round, this right here is the picture of what they think it looks like. Okay, so here you have the North Pole, and so here is somebody who's out on the ocean, and this line that you see right here, okay, that's the horizon line. So if you point your arm at the horizon, that's this line, and then the other arm here is going to be pointed at Polaris. Okay, so that's this line right here. Now Polaris is actually directly above the North Pole, but because Polaris is 400 light years away, 400 light years, let me do that. Okay, it's so far away that if somebody at the North Pole pointed their arm at Polaris and somebody elsewhere pointed their arm at Polaris, Polaris is so incredibly far away that these two lines would be perpendicular, even though in reality, they're slightly different. But 400 light years is virtually infinite, right? So these two lines are going to be parallel, no matter where you are on the Earth. Okay, so the angle right here, that is what we're going to call Polaris's altitude. So altitude, we're going to use that for angle. All right. So people who believe that the Earth is round, they say, well, okay, so this makes sense here. That as you go south, the angle is going to get smaller, and when you get down to the horizon, okay, so this is when you get down to the equator. So this line here is going to be your horizon line, but that's also the line to the North Star. So at this point, the North Star is sitting right on the horizon. And when you get down below the horizon, or below the equator, here's your horizon line. So Polaris is going to be below the equator, so obviously you're not going to see it. So people who think that the Earth is round, they say, okay, this proves that the Earth is round, okay? And so all you need to do for question number 2 in the homework tonight is basically just summarize what I just said. In your own words, type that into the textbooks here. Basically what I just said right there. Just prove to me that you were listening. Okay, now, here's where it gets fun. So people who claim that the Earth is round, oh my goodness, why is my image not showing up? Oh no, it showed up great yesterday. Let me refresh the page here. Ah, okay, good. All right, this time it showed up. Yay. Okay, so one of the things that me and my friends of the Flat Earth Society love to do is to tweak people. We love being trolls. Okay, so some people say if the Earth was flat, then what we just described wouldn't happen. Okay, so let's say that we're the North Pole here. Let me turn on annotation again. Okay, so this ship right here is the North Pole. And so they point one arm at the horizon, the other arm at the North Star, and they measure 90 degrees. So if the Earth is flat, then as you head south from the North Pole, the angle should never change. Because remember, Polaris, as far as we're concerned, is infinitely far away, right? So no matter where you are on the Earth, the angle between the horizon line and the North Star should always be 90 degrees. And so people say, ha ha, we just proved that the Earth isn't flat. Well, me and my friends of the Flat Earth Society, we don't give up that easy, okay? We have a comeback for that, right? So, oh, by the way, what I just described, if you type that into the box here, bingo, there you get the next question right. Okay, so now let's move on to the next one. So me and my friends of the Flat Earth Society, we love trolling people. So we say, we have an explanation for that. Okay, that doesn't in fact prove that the Earth is not flat, wink, okay? Because this is what we claim that the Earth looks like, okay? Our comeback is that Polaris is actually not infinitely far away. So your junior high school teacher who told you that Polaris was 400 light years away, your junior high school teacher was wrong, okay? Wink, okay? Polaris is actually not in 400 light years away. It's actually just a few thousand miles above the North Pole. So it is sitting up above the North Pole. So then as you travel south, okay, the angle the angle between the horizon and the Polaris, this angle right here, okay, it is in fact going to get smaller, Okay, so when you say that explorers head south and the angle gets smaller and therefore that proves the Earth isn't flat, well, me and my friends of the Flat Earth Society, we say, that doesn't prove diddly squat, okay? Because this is what we think the Earth looks like. So neener, you haven't proven that the Earth isn't flat. You guys see where I'm coming from? Let me pause for just a second here. Does anybody have any questions about what I've just covered here? Does it make sense? You see why I like being a member of the Flat Earth Society. It's really fun trolling people. Okay, so what I just described here, if you just type it into the text box here using your own words, I'll give you credit. Just prove to me that you're paying attention, basically. That's all I want. Okay, let's move on to the next one. Okay, so the round Earth people, they say, well, okay, how about another argument? Here's an argument. Remember how we said that the further south you go, the lower the Polaris becomes, and then once you get to the equator, and actually once you get below the equator, you can't see Polaris anymore. So that proves that the Earth isn't flat. Do you see why? You see why they would say that? Let me go back. Let me go back to the previous page here. Okay. So the round earthers, they say to me and my friends, they say, hey, look at your diagram. Can you see a problem with your diagram here? So yes, the angle gets smaller, and so you go out further and it gets smaller still. You go out further and it gets smaller still, but you see it never goes to zero. And it certainly never goes below the horizon. So the round earthers, they say to me and my friends of the flat earthers, they're saying the fact that Polaris disappears when you go below the equator, that proves that the Earth is not flat. Do you see how they've got a pretty good argument there? Yeah. So you might think, aha, well, we've disproven the flat Earth theory. Well, again, me and my friends of the Flat Earth Society, we don't give up that easy. We have a comeback for that one too. Okay, so right. So here's where you explain that. So let me go to the next page here. Okay, so this now is our comeback for why it is that you can't see why you can't see Polaris when you get below the equator. This is the picture that we draw. And we say, well, the air is actually not completely clear. And by the way, that's true. I mean, I've spent a lot of time out on the ocean. I mean, I took off 1 year, in fact, and spent an entire year just sailing around to various places all over the Earth. I've spent a lot of time in the ocean, and even when there aren't any clouds, there's always a light level of haze, especially down near the horizon. So that when you're, well, let me turn on annotation. Okay, so if you're at the North Pole, and you draw a line from you to the North Star, that distance is not very far. So you're not looking for very much haze. The further south you go, the more haze you're looking through. You get really far south, that line has to travel through a whole lot of haze. And so me and my friends of the Flat Earth Society, we say, the fact that Polaris disappears doesn't really mean anything. It just, the reason you can't see it anymore is because of all the haze. It's not because the Earth is round. So neener again, you still haven't proven to my satisfaction that the Earth isn't flat. Okay. All right. So again, if you just summarize in the box here what I just said, then you're good. Okay, so we're going to have to find another way, or actually you are going to have to come up with another way. Remember, I think the Earth is flat, wink. Your job is to prove to me that it's not. Okay, so here is my strategy for how we're going to do this. And there are other ways. There are many other ways, because the Earth really is not flat. Okay, it's obviously round. And pretty much all of my friends of the Flat Earth Society recognize it's actually round. We just enjoy trolling people. Okay, so here is a strategy that you could use. And this is the one that I want you to use because it illustrates a technique that we are going to be using all year long. Okay, and this is a great way to illustrate how physicists do physics, how scientists do science. Okay, so what we're going to do is we are going to come up with a hypothesis, which in this case is going to be the flat Earth hypothesis. So we're going to make a hypothesis. We're going to say, okay, at least for the sake of argument, let's assume for a minute that the Earth is flat. Okay, and then what we're going to do is we're going to come up with an experiment that we could conduct that could possibly maybe disprove this theory. And so here's what the experiment is going to look like that we're going to do. And this is just a thought experiment for right now. So we're going to imagine that we stand at the North Pole and we've got one arm pointing at the horizon and we're going to point the other arm at the Polaris and we're going to measure that angle. And if we're standing at the North Pole, obviously we're going to get 90. But then we're going to walk further south. In fact, let me scroll up here. Okay, so after we make the measurement at the North Pole, we're going to walk southward for many, many miles. And every once in a while, we're going to stop, turn around, and we're going to point one arm at the horizon, the other arm at the Polaris, and we're going to find that we get the further we go, the smaller that angle becomes. And we're going to keep track of those data points, and we're going to graph them. And we're just going to keep on going. Okay. All right. So this is an experiment very much like the ones we did last week. In fact, I purposely did the ones last week in order to prepare you for this one. So the independent variable in the experiment that I just described is going to be our distance from the North Pole. Okay, that's our independent variable. How far are you from the North Pole? Our dependent variable is going to be the angle of Polaris above the horizon, which I'm going to call the altitude. Okay, so let's pause for a second and let's take a poll here. So I want to know right here. So we know what our independent variable is, we know what our dependent variable is. So I want you to answer the same questions that we asked last week. I want you to make a two-part hypothesis. Do you think that there's going to be a direct relationship or an inverse relationship between these two variables? Do you think the relationship will be linear or nonlinear? Now, the important thing is, remember, I see some of you already started answering. This is assuming that the Earth really, truly is flat. Okay, that's important. In fact, tell you what, I'm going to end the polling here, and I'm going to restart it because some of you answered before I started. We are going to ask these questions with the assumption that the Earth is flat, because that might change your answers. Okay, so let's try again. Those of you that answered once, I just erased it all, so everybody has to start new. So if the Earth really truly is flat, would you expect a direct relationship or inverse relationship? Would you expect to be linear or nonlinear? Everybody has to answer. I'm going to pause for just a second here. Oh, the results are very interesting so far. Oh, very interesting. Yes, keep on going. Okay, so 2 of you haven't answered yet. Actually, okay, all right, good. Okay, so let's take a look at the results of the poll. All right, so the majority of you said it's going to be an inverse relationship. 5 of you said it's going to be direct. And the majority of you said it's going to be linear. Only 5 of you said nonlinear. Okay, so this is very interesting. Let me turn on the whiteboard. Okay, hang on a sec while I get whiteboard up. Okay, and clear that. Okay, so let's draw a picture here. So remember, we are assuming that the flat Earth hypothesis is correct. So here's the flat Earth, here's the North Pole, here's Polaris, not infinitely far away. Okay, so at the North Pole, you guys agree we're clearly going to get 90 degrees. Okay, as we go further away from the North Pole, we're going to get an angle that's smaller. We go further away still, we're going to get an angle that's smaller. So as the independent variable gets bigger, the dependent variable gets smaller. So those of you who said that you thought this was going to be a direct relationship, go back and rethink what it means to be direct or inverse, because I would hope that everybody would see this has clearly got to be an inverse relationship. As our independent variable gets bigger, the dependent variable gets smaller. Now, most of you said that you thought it was going to be a linear relationship. Ah, gotcha. Okay. Okay, let's graph this. Let's say that we do a graph. So at 0, here we get 90 degrees. So this is the point 0, 90. Now, we know that as we head south, it's going to trend downward, right? Now, if it was a linear relationship, and if it starts off trending downward, well, it's going to continue going downward, right? Because a straight line, once it starts downward, it's going to continue downward forever. So if it was a linear relationship, there would be a point here where it reaches 0. And in fact, there would be where it gets negative. But if the Earth really truly is flat, will it ever reach 0? Hopefully you see no. So no matter how far you get out here, okay, that angle is never going to reach 0. Okay. Now, me and my friends at the Flat Earth Society, we're going to say, well, if you get too far away, you're not going to be able to see Polaris anymore because of the haze. But it'll never, ever going to reach 0. It just disappears because you can't see it anymore, but the angle never reaches 0. Okay, so if you've got something that starts off trending downward and you know that there's some lower limit that it can never get to, by definition, it must be nonlinear, okay? So this is the kind of thing that I would put on a test. And looking at the poll results here, I'm seeing that a lot of you would miss this if I put it on a test. This one should clearly be an inverse relationship, and clearly it's got to be nonlinear if the Earth is flat. Okay, so those of you that said otherwise, maybe you didn't realize that that's the assumption I'm working on here. I'm working on the assumption that the Earth is flat. Okay, so let me go back to sharing this again. Okay, so the way that we're going to find out whether or not the flat Earth hypothesis is correct, okay, is we're going to figure out what the graph of the experiment would have to look like if it's flat. And then we're going to compare that with data that people have actually taken. And we're going to see if the measurement data fits with what the equation would have to look like if our hypothesis is true. And in fact, I have some terminology that we're going to be using a lot throughout the year, and so I want you to get used to it. We're going to talk about mathematical models. So we're going to take our hypothesis, the flat Earth hypothesis, and we're going to say if our hypothesis is true, then the experiment that we're describing, the data has to be inverse and nonlinear. And in fact, we can even figure out what the equation is. So that equation is going to be our mathematical model. And so we're going to assume, we're going to do this twice. We're going to do once, assuming that the round Earth hypothesis is correct. And we're going to do it another time where we assume that the flat Earth hypothesis is correct. And then finally, what we're going to do is we're going to compare the results of our mathematical model, basically the predictions. We're going to compare that with actual measured data. So you see why I like this activity? Because this activity that we're going to do here is a great way to illustrate the way that science is actually done. So using this technique, hopefully we can find out, is the Earth really flat or is it not? Okay, so no questions to answer on this page. This one's just an information page. All right, so here is the next page. And okay, so here, again, my illustration is not showing up. Why is, oh, it's just the internet's just being slow. Here, let me, oh, there it comes. Okay, there we are. Okay, so let's start with the round Earth hypothesis, because that's the one that most of you guys claim to believe, even though you haven't yet proven to me. Okay, so if the Earth really truly is round, okay, now I'm going to ask the same questions that I asked before. Is it direct inverse? Is it linear or nonlinear? So let me start my poll here again. Okay. Now this time, remember, the assumption this time around is that the Earth is round. Okay. So if the Earth is round, when we do our little experiment here, is it going to be direct or inverse? Is it going to be linear or nonlinear? Okay, so about half of you have answered. The rest of you still need to answer. Now remember, this is all anonymous, so if you're not sure, go ahead and just type it in here. Okay, I need 2 more people to answer. 1 more. Okay, good. All right, so let's see what you said. Again, I still have 6 of you who said that it's going to be a direct relationship. Guys, think about it. Let me turn on annotation here. Okay, so if the Earth is round, that's the assumption we're working on. So you're sitting here at the North Pole. So there's your horizon line. The North Star is directly above you. So you're going to get 90 degrees. As you head further south, the angle gets smaller. Okay, so the further away from the North Pole you get, the smaller the angle becomes. Is that a direct relationship or is that an inverse relationship? Well, 11 of you recognize that's an inverse relationship, but 6 of you thought it was a direct relationship. So we obviously need some more practice with this. This one should have been obvious that it's an inverse relationship. Okay. Now, as far as the linear or nonlinear part goes, 11 of you said it was going to be linear. 5 of you said it's going to be nonlinear. This one may not be completely obvious, but if you think about it, it is possible to answer this with certainty. If you look at our little angle here, so our latitude, you know, the angle how far above the horizon, above the equator, our latitude here is this angle. And the angle that we're measuring, the thing that I'm calling Polaris is altitude, is this angle up here. Okay. It's possible to prove that those 2 angles are equal. And I'm not going to take the time to do it here, but in your math class, hopefully when you learned about, you know, right angles and vertical angles, remember all that good stuff about vertical angles and alternate interior angles and all that fun thing. Okay, using the techniques from your math class, it's actually easy to prove that these 2 angles must be the same. Now, if that's true, then what that means is for every 1 degree that you go south in latitude, Polaris's altitude will go down 1. And it doesn't matter whether you're up here in the north part or down here in the south part, 1 degree of latitude change is always going to give you 1 degree of altitude change. So based on that, it is possible to prove beyond doubt that the relationship is in fact linear. So if we were to graph it, so we start off here at 0, 90. So it heads off downward and it will continue down in a straight line. There will be a point where it will reach 0. And in fact, it will continue on down to be negative, which actually does make sense because if you're down here in the southern hemisphere, here's your horizon line. So remember, if you're in the southern hemisphere, this is you standing right here. That's a terrible picture of you standing right there. So the Polaris is below the horizon for you. So the angle is in fact negative, okay? So this sketch right here, this is what the relationship would look like if the Earth is round, okay? So we've got 2 different sketches here. This here is the round Earth theory. And then down here, I'm going to put the flat Earth theory. Both of them start at the point 0, 90. Both of them start off heading downward. But the important thing is that the flat Earth model, the prediction of the flat Earth hypothesis is true, it has to be a non-linear curve, whereas the round Earth model has to be a linear curve. So this is how we're going to answer the question. We're going to take these 2 different models and we're going to compare them with actual measured data. And we're going to see which one matches the actual data the best. Okay. So let me get rid of this. Let me clear my screen. Okay. And okay, so in the homework tonight, you're basically going to retake the poll that we just took, but this time get the answers right, please. Okay. So clearly it's got to be an inverse relationship. And then on the next page here, it's going to ask whether it's going to be a linear or nonlinear relationship. Okay. So clearly if it's the round Earth, remember we're talking about the round Earth hypothesis here. So if the Earth is round, it's got to be it's got to be a linear relationship. And then here for the flat Earth, whoops, okay, oh, I'm sorry, and then sketch the graph. Okay, so I just got through sketching the graph for you. I'm actually giving you the answers here. Don't get used to this, guys. I'm not going to be doing this all year long. But for today, because this is a new idea for many of you, I'm actually just giving you the answer. So all you have to do is basically just kind of take notes and pay attention. So I just got through sketching what the graph would look like if it's round. So all you have to do is you need to sketch it, and then do it on a piece of paper and then upload the file. Take a picture of it and upload the file. Or you can do it in a computer graphics program, like Paint or whatever. If you want to do that, that's okay too, right? Now, here's something that's important that we haven't done yet. I want you to find the equation of the line. Now, this is a really important part of the assignment here. So let me turn on annotation again. Okay, and let me redraw our sketch here. And by the way, I haven't looked in the chat box for a long time. Okay, oh good, it's showing me the chat box this time. All right, so I'm not seeing any comments in the chat box, so I'm going to go ahead and keep on doing here. Okay, so our independent variable here is the distance from the North Pole. Our dependent variable is the angle. So we know it's going to start at the point 0, 90. Because, oh, that doesn't look like a 0, does it? Let's try that again. Okay. Okay, so we know that if we're at the North Pole, so our distance from the North Pole is 0, we know that the angle we're going to measure there is going to be 90 degrees. Okay, and we also know that when we get down to the equator, it's going to be 0. Okay, now, oh, I see. I didn't give you some important information here that you need to know. I'm going to have to edit this. So write this down. This is really important. When you're at the equator, okay, the distance, okay, hang on a second here. I don't have this memorized, and I want to make sure I don't give you the wrong answer here. The distance to the equator is an important number that you need to know. And I thought that I had included it in here. Okay, so 6,215. Okay, so write this down. You're going to need to know this. Okay, so 6,215, 0. That's the coordinates of this thing. So from the North Pole to the equator, that distance right there is 6,215 miles. Okay, so when we do our graph here, we know the coordinates of 2 points. We know this point here up at the top here. This is 0, 90. The point down here is 6,215, 0. So there's the line. So if you know 2 points, you should be able to figure out the equation of the line. Okay, so I'm not going to help you with this one. I'm definitely not going to just give you the answer here. I'm hoping that you guys are good enough at math that you can find the equation of a line given 2 points. Okay. So I'm going to trust that you can do that, and I'm going to skip on from there. Okay, so in the text box here, write the equation once you get it. Okay, now let's go on to the flat Earth hypothesis. Okay, so we're going to switch hypotheses now. We're going to say, okay, now we're going to assume that the Earth really is flat. So do we expect a direct or an inverse relationship? So hopefully you guys can get this one right. We've already talked about this one. And then the second part of it is, if the Earth is really flat, would you expect it would be linear or nonlinear? And again, hopefully you guys can get this right because we've already talked about it. So these should be easy homework points for you. Okay. And then we need to sketch the graph, okay, which I've already sketched it for you. So basically, I've given you the answer to that one. Okay, now this next one here we haven't yet talked about. We're going to have to find the equation of the graph. All right, so let me turn on annotation again. So I'm going to go ahead and sketch the graph for you like we did before. But remember, this time we're assuming that the Earth is flat. So here's your distance from the North Pole. Here's theta. We start off at the same point that we started off before. The coordinates are going to be 0, 90. And it is going to start trending downward just like it did before. But if the Earth is flat, that angle will never exactly reach 0. So it's going to approach 0 asymptotically. So how can we figure out the equation of this curve if this is all we know? Well, it turns out we do need to know something else. Okay, this by itself is not enough to find out the equation of the line. Okay, so I'll turn off the annotation temporarily. Okay, so I have not yet given you enough information to find out the equation, but let's go ahead and let's do it now. Okay. So what you guys could do tonight, if you wanted to, is you could make up a little tool like this one right here, and like you're seeing on the screen here. So what I've got is I got a protractor, I got a straw taped to the top, I've got a string with a weight on it. And so if I were to go outside tonight and find the North Star and look at it through the straw and then see what the angle is on the string here. And now this protractor is set up so that if I'm looking at something on the horizon, the protractor is going to say 90 degrees. But that's not what we want, because that would correspond to be 0. So basically, if you just take the difference between the number shown on the protractor and 90 degrees, you just subtract 90 from it, then that'll be the angle. So this would be 0 here, this would be 10 degrees, 20 degrees, 30 degrees. So if I were to go outside tonight, or if you were to go outside tonight, and measure the angle of Polaris above the horizon, that would give us the missing information that we need in order to figure out the equation. Okay, so in order to make things a little easier, I'm going to give you the number here. So let's suppose that we do this from Salt Lake City, and what you'll find, well, depending on where in Salt Lake City you are, but if you're in the place in Salt Lake City where we were when we measured it, you'll get 40.75 degrees. Now, I got to be honest here. Using this protractor, you're not going to be able to get the number to that level of accuracy, to 1/100th of a degree. There's no way you can get 1/100th of a degree of accuracy using this tool. With this tool right here, the best you could hope for would be to get maybe to the nearest 1 degree, right? But if you use this tool right here, okay, this is a sextant. This is what I use when I'm out on the ocean during the summertime, which is how I spend my summers. This is a sextant, and I'm not going to take the time to explain here how it works, but using this, you can measure the angle of any star, and you can get it with an accuracy of 1/100th of a degree. And this is an amazing tool. And if you want later, I can talk to you how this works. It's very cool. So let's suppose we know that if we're in Salt Lake City, the angle of Polaris is 40.75. And let's also suppose that we know that the distance from Salt Lake City to the North Pole is 3,401 miles, okay? Now we know what we need. So we know one of the points here. We know that, oops, sorry, I got to turn on annotation again. So we know that this point right here, the coordinates of that point are 3,401, 40.75, okay? So now we can find out the equation of that curve, okay? Now to do that requires a knowledge of trigonometry. And I realize that some of you learned trigonometry last year, but you may have forgotten a lot that you learned. And a few of you, maybe you haven't even learned trigonometry yet. So if you are one of those people who hasn't learned trigonometry yet, and you're saying, oh my goodness, this is crazy, I can't handle this, don't worry. We're going to teach you what you need to know. So even if you haven't yet learned about trigonometry in your math class, we'll teach you what you need to know. So let's go through together how we might get that equation. Okay. Well, it's going to be a two-step process. Step number one is we need to figure out if the Earth really truly is flat, then that means that Polaris is not actually 400 light years away. Polaris is actually something much, much, much less than 400. So we need to figure out what is H here. Okay, so I'm going to say H equals question mark. So we need to figure out how high above the North Pole would Polaris have to be in order for the flat Earth hypothesis to have any hope at all of being true. Now, I'm hoping that some of you guys remember your trig well enough. So what we've got here is we've got a triangle, and we know that this angle right here is 40.75, and we know that this side here is 3,401. Could any of you use your trigonometry skills to tell me what is H? I'm going to pause for a minute, give you a chance to think about it. I want everyone who's learned trig, everyone who knows about sines, cosines, and tangents, I want you to take a minute and see if you can figure out what is H based on the information that we've gotten here. So this is a right triangle, it's 90 degrees. We know this angle, we know the adjacent angle. What we want to know, or we know the adjacent side, I mean, and what we want to know is the opposite side. Anybody got any ideas how we could do that?
Yeah, you could use Sohcahtoa.
Sohcahtoa, I like that.
Yeah.
Okay, so Sohcahtoa, for those of you who don't know, so it's spelled S-O-H-C-A-H-T-O-A. So what it means is that the sine is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over adjacent. So if this is the angle that we know, and the side we're interested in is the opposite side, and this side is the adjacent, which one of these three friends here is going to help us out? Sine, cosine, or tangent? Which one's the one we want?
Would it be tangent?
Tangent would be it. Okay. So we know that the tangent of an angle is equal to the opposite divided by the adjacent. And we know what the angle is. Okay. We know the angle is 40.75. So we know that the tangent of 40.75 is equal to the opposite, which is the thing we're looking for. So let's just call it H, divided by the adjacent, which is 3,401. So if we just multiply both sides by 3,401, what we'll find is that 3,401 times the tangent of 40.75 equals H. So somebody get out your calculator and punch it out and tell me what you get.
I have it already. I did the calculations a little bit earlier. What I got was 2,930.49 if rounding to the nearest hundredth.
Okay, so let's just round it to the nearest 1 mile. Okay, so does somebody second that motion? 2,930? Yeah. Okay, good.
Yeah,
we have a second.
Thing.
Yep.
All right, any opposed?
Same.
Okay, so no opposed. All right, the motion passes. Okay, so now we know how high above the Earth, how high above the North Pole Polaris would have to be in order for the Flat Earth Society to have any hope of being right in thinking that the Earth is flat. Okay, good. So this is a really important thing. So 2,930, let's write that down. Okay, so now that we know that, now we can go on to the rest of the problem here. Let's see, okay, so we just found the answer to this question here. And again, I'm giving you the answers here. Do not get used to this. I'm not going to keep doing this as the year goes on. I want to start off, I want everybody to have a good feeling for how this goes starting off. Okay, so now step 2, now we need to come up with the equation. All right, so your assignment is to find theta as a function of d. Now I see we don't have a whole lot of time left. So let me just go ahead and do this for you because I don't want you to freak out. I don't want students saying, oh, I don't know how to do any of this. This is crazy. This is the wrong class for me. I need to switch into Miss Whitbeck's class. Don't worry. We will do this slowly together as a class. So I'm going to help you with this one. And we're actually going to use the same equation we did before, except this time, what we're going to do is we're going to say that we want to find the equation not for Salt Lake City, but anywhere. So this D value right here is not going to be Salt Lake City. This could be anything. And this theta here, well, we don't yet know what it is because it depends on what D is going to be. So theta is going to be our dependent variable now. D is our dependent variable. But this time we do know what H is. This time we know that H is 2,930. So we go back to our same equation that we just got through using where we said that the tangent of theta, now this time I'm going to leave it as theta rather than putting a number there because I want to keep it generic, is equal to the opposite side, which we didn't know before, but now we do. We know that it's 2,930 divided by the adjacent side, which this time we don't know. That could be anything. So I'm going to leave it as D. All right. So if we want to find theta as a function of D, what do? So I look at my equation, I see I've got tangent theta. How do I get rid of that tangent? Do I divide by tangent? Is that how it works?
Inverse tangent.
Ah, okay. So you're saying dividing by tangent is not going to work because it's not tangent times theta, it's tangent of theta. So I can't divide by tangent. So what I have to do is I take the inverse tangent. So if I take the inverse tangent, okay, inverse tangent kills tangent, just leaves me with theta. But if I do that to left side, I have to do the same thing to the right side. Okay, those are the rules of mathematics. Whatever you do to the left side, you got to do the same thing to the right side. So that means I have to take the inverse tangent of 2930 divided by D. Okay, there you are. That is the equation that we're looking for. Now, we're going to be putting that into Desmos. And Desmos actually does allow you to use theta and D and whatever you want to call it, but most people are more familiar with having your independent variable be called X and your dependent variable called Y. So when we put it in Desmos, we're going to say Y equals the inverse tangent of 2930 divided by our independent variable, which we know is D, but Desmos might be happier if we call it X, okay? So this is the equation that we're going to put into Desmos. Okay. All right. So we write that down in our notes. So Y equals inverse tangent of 2930 divided by X. All right. So let me clear that. And, all right. And so in the text box here, just type the equation. So remember, don't get used to this, guys. I'm not going to keep doing this all year long. I'm going to make you figure out the answers later. But for right now, I'm just going to help you. Okay. So we are running really low on time, and I anticipated that we probably would. So I'm going to stop here for today. So next time we meet, we're going to take these equations, we're going to put them in Desmos, and next time we meet, I'm going to give you the data that people have actually measured from various places here in Utah. And we're going to see, does the flat Earth hypothesis, does the mathematical model that we created for the flat Earth hypothesis, does that fit the data? Or does the round Earth data fit it better? And we're going to make a bunch of decisions there. But I'm going to save that for next time because we're running a little bit low on time here. So like I've said before, and I'll say one last time, don't get used to what happened today. Today, I basically gave you the answers. So if you were just paying attention and taking notes, all you have to do is just fill in the spaces on Canvas, send it in, and you don't have to do a whole lot of thinking today. But that's going to change later. Okay, before I break off here, does anybody have any questions about what we've talked about?
Just real fast. So
Uh-huh.
is this recording going to be on your Canvas page, just if we need any help?
Yes. What I do is, I have 3 different physics sessions. I record all 3 of them, but I don't put all 3 of them up on Canvas. That wouldn't be much point in that. So, so I will put one of them up on Canvas, but I'm not going to do it today. I'm going to wait probably until, in fact, I will wait until tomorrow. So sometime tomorrow, I will put up either the recording that we just have right here or one of the other classes. Okay.
Okay.
Any other questions? So I'm going to take roll one last time, but this time, rather than typing in here or not here, what I want you to do is I want you to give me some indication of how comfortable you are with the material that we just covered. So either say something like, I got this, or say something like, I'm a little shaky, but I think I'll get it. Or say, man, I did not understand what we did today. Okay. And okay, yeah. So Derek decided to give it a number. I like that. Okay. So you could do that. So on a scale of 0 to 10, tell me how comfortable you are with it. I like that. And if any of you would like to stick around after the rest of the people log off, I'll be glad to talk with you one-on-one, or right now. I mean, if you have a question right now, go ahead and ask right now. Okay. And then once you, so if you're comfortable with this and you don't need any additional help, go ahead and just log off and get working on Canvas. Those of you that think you're a little shaky about what we talked about, if you're willing to stick around after everybody else logs off, I'd be glad to give you some one-on-one help. So I see a lot of people disappearing here. Tell you what, I'm going to turn off the recording. So if you're one of the people who's feeling a little shaky, but you don't want your conversation with me to be recorded, I can deal with that. I'm going to stop the recording right now, and then we'll have a private conversation.